Welcome to the 14th annual eBeam Initiative meeting. I'm Aki Fujimura. I'm CEO of D2S Inc., which is the managing company sponsor of the eBeam Initiative. This is an annual event that usually takes place at SPIE Advanced Lithography. This year is kind of strange again because of COVID. SPIE Advanced Lithography is a little bit delayed, but we're having this meeting in originally scheduled time. I hope everything goes back to normal next year. We'll see what happens, I guess, right? So the first thing I wanted to talk to you about today is the deep learning survey. We started our annual deep learning survey last year, and this is the second year. And several new entries went in. So please go take a look at ebeam.org. When you look there, you see that the big theme is SEM. It makes sense because deep learning is really good at image processing. There's a lot of pre-built libraries that's available. So it's a relatively good project to start deep learning on. And a lot of people are working on it clearly. One thing that I would note is that if you're doing a SEM-based deep learning project, then having a digital twin is very helpful, especially as you try to go from mature, from a prototype stage to a production deployment. And because deep learning is programmed by data, as you notice something not being quite right about, let's say, defect categorization or something, you need to be able to create new data, new pictures that they call it disambiguation, being able to differentiate between this is category A, this is category B. You need to present deep learning with a whole bunch of new pictures of examples of A and examples of B and examples, ones that are perhaps confusing, that looks like A but is B or something like that, right? So, being able to do that requires new data to be created on the fly. And as you know, that's very difficult in our industry with SEM pictures. One, because of confidentiality of data. There's no such thing as a ImageNet version of SEM for our industry. And then also, even if you were committed to go take new pictures, it takes a long time. It's very expensive, right? So much better alternative, just like the auto industry does, is to use digital twins. So as we see SEM being a popular topic for deep learning, and I think we should be, as an industry, paying more attention to digital twins for SEM so that we can do these deep learning projects better. Okay. Moving on to the eBeam initiative itself, we're a body that exists to help the industry, help the mask industry, both in really promoting what an important set of work and interesting set of work that we do in the industry, and also collaborating together, a forum to work together, and that's what we exist for. We have 3 new members this year. We have ESOL from EUV Solutions, and is what it stands for. They are a pioneer in measurement systems for EUV. They were founded in 2018 in Korea. CEO is BG Kim, and many of us in our industry are very, very familiar with BG Kim, a very famous guy. The second company is Fractilia. Also a very famous guy, Chris Mack, is a founder, and they are a leader in stochastics metrology and control solutions. They were founded in 2017 in Austin, Texas. And then the third new member is HJO Lithography. This is the consulting firm, lithography consulting firm that was founded by Dr. Harry Levinson. And speaking of Dr. Harry Levinson, really hearty congratulations to Harry for being the recipient of this year's Frits Zernike SPIE Award for microlithography. So we're going to have three presentations today to talk about that. Donis Flagello of Nikon, he is the 2017 Frits Zernike Award winner. And then Chris Mack of Fractilia, we just talked about, 2009 Frits Zernike Award winner. And then we'll hear from Harry, who is the 2022 Frits Zernike Award winner. So we're incredibly honored to have this incredible lineup of people. Please enjoy.
Hello. If you don't know me, my name is Donis Flagello. I am currently the CEO and President of Nikon Research Corporation of America. But I also happen to be the current chair of SPIE's committee for the Frits Zernike Award for Micro and Nano Lithography. I'd like to spend the next few minutes telling you about the award and our latest award winner. The SPIE Frits Zernike Award for Microlithography is our highest award and recognition we have for advanced lithography. It is presented for outstanding achievements and accomplishments, especially those furthering the development of semiconductor lithographic imaging and patterning solutions. The award was started in 2004, and to date we have 19 recipients. It is my great pleasure and honor to announce that Dr. Harry Levinson is our 2022 Frits Zernike Award winner. Now, many of you know Harry. Almost every lithographer knows Harry's name through his books, his publications, presentations, courses, and discussions. Harry spent most of his career working in lithography. He started out in AMD, managing their lithography division, and then moved on to Global Foundries. For many years, Harry also served as chairman of the Lithography Technology Working Group that created the Litho chapter for the ITRS roadmap for semiconductors. Among his many roles of service to SPIE, Harry also has been chair of many SPIE committees. He has been an SPIE board member and is the current editor-in-chief of SPIE's JM3 journal, which is the Journal of Micro and Nano Patterning. Harry has promoted every aspect of lithography, including deep UV, immersion, multiple patterning, eBeam, and EUV. He is the author of 3 books on lithography, including his latest on EUV. He has countless published articles on topics ranging from thin film optical effects to metrics for imaging to overlay and process control. And on top of that, he holds 70 patents. Harry has a very generous character. He is a mentor and a leader in our community. Please join me in congratulating Dr. Harry Levinson as a 2022 Frits Zernike Award winner. Thank you.
Hello, my name is Chris Mack, and it is my great privilege and honor to congratulate Harry Levinson for winning this year's Zernike Award for Microlithography, presented by SPIE. I hope you've already listened to Donis Flagello's video. Donis is the chair of the Zernike Committee and gave a very nice resume of Harry and why he so richly deserves this award. What I'd like to do is make it a little personal, talk about my experiences with Harry very briefly, and why I also agree that this award is richly deserved. I first met Harry at an SPIE microlithography conference many years ago. I won't say how long. It's been a long time. And he was teaching a class. I was new. He was actually pretty young then too, but still teaching a class on that Sunday before the beginning of the conference. And I took that class to learn as much as I could, drinking from a fire hose, as all young lithographers do the first time they go to SPIE. And it was tremendous. He was a great instructor. And one of the things I got from that is this book. This book is remarkable. I have referred to it so many times that it's like falling apart like crazy because I always go back to this when I want to think about how to apply statistics to lithography. Harry's a great guy. Of course, I first met him by reading his name on the many important papers that he has read. But then when I got to know him personally, It's always a pleasure. He's very honest up front, methodical, and of the highest integrity in all of his interactions. He cares so much about this field, and I do too, which is why it's great to work with people like that. Harry, congratulations. I've also been asked to give a few words about what I think of the future of lithography. Well, I'm not a man of few words. I talk too much. But I'll very, very briefly say just a couple of things. As my good friend John Beafor likes to say, determinism is dead. The world going forward at all advanced nodes, especially the EUV, is a stochastic world where one of the major components of all variability is the fundamental randomness that happens at the atomic scale. And our feature sizes are so small, the volumes of interest that we care about, little bitty cube of resist, is small enough that the events that happen rely on counting statistics rather than continuum statistics like we used to think about. So that's the world we live in. That's the world I have been trying to study. And what we all need to do is similar to what I've been trying to do and still trying to do for these past 15 years or so, is put my mind into a stochastic mindset. We tend to, as engineers and scientists, tend to have a deterministic mindset where, given an input, this is the output you would expect. And as a modeler, a long-time lithography modeler, that's the way I've thought about the world for such a long time. We just need better models, and then we can predict what's going on, but you can't, at least not in a deterministic sense. Today, to predict what's going on, you have to think stochastically. Randomness is a fundamental part of the lithography process at the smallest length scales, which are the length scales we deal with today. So that's the future of lithography in my mind. How we deal with those stochastics is a great unknown. It's going to be a fun ride to watch it happen. So that's my 2 minutes and 2 cents worth. I hope you got your money's worth. Thank you.
Well, it really is an honor to be recognized by one's colleagues and peers. And for a lithographer, I think that that is what the Frits Zernike Award represents. Since there are many quite accomplished lithographers, this is particularly gratifying. The description on the SPIE website that details the reasons why I was given the Zernike Award mentions several specific contributions from early in my career, such as the image log slope and problems addressed having to do with mask defect printability and some problems in thin film optics. When I started in the semiconductor industry, it really was an interesting time, particularly for lithographers. Prior generations of lithographers had addressed some very important practical issues. For example, vacuum vapor prime had been developed, and this improved the adhesion of resist to substrates that proved very valuable as we made smaller and smaller features, and it was increasingly difficult to get them to stay on the wafers. There are other problems such as resist edge beat that got addressed. But if you look at the proceedings from conferences in lithography from the 1970s and early 1980s, frankly, you wouldn't see a lot of equations. But that was changing at the time I entered the semiconductor industry. For example, the pioneering lithography simulation program Sample had just been introduced and made available, and it was there for me to use. And that was really pretty important because I could do lithography simulations very early on and didn't have to spend months and months programming and debugging a lithography simulator of my own. And I used it right away. The metric, the image log slope, was basically a concept, but its value couldn't really be appreciated until it was tested with some very specific examples. And for that, one needed lithography simulation. And simulation and computational lithography has continued to be very, very important over the years. It went from the basic simulations of those early days to things like resolution enhancement techniques and optical proximity corrections. And now we see very sophisticated implementations such as inverse lithography technology. Something else that was very important in my career, again, fairly early on, I was actually made manager of a lithography department. And it's been my good fortune to have a number of really, really excellent engineers in my group. Several of them are SPIE fellows, and actually 2 of them were prior recipients of the Frits Zernike Award. After I first came up with the image log slope, we used it quite a bit at AMD where I worked at the time, but we didn't publish it because the utility of the metric was appreciated, and well, we didn't want to share it with the competition. But at one point, my colleague Bill Arnold and I noticed that quite a bit of money was getting spent on X-ray lithography. And we really didn't think this was a good wise use of resources. And so we decided that the best thing to do was to write a paper arguing that optical lithography could be extended, quite a distance further. And in order to make a good solid argument, we wanted to use the image log slope. So we got approval from our executives to publish the metric along with the paper. In that paper, we made something that at the time was considered very, very aggressive. We said that optical lithography would go all the way, at least, to half a micron in size. And at the time, that was considered pretty outrageous. But of course, we did half micron and quite a bit beyond with optical lithography, as we went through shorter and shorter wavelengths and larger and larger numerical apertures. And at each wavelength and new generation of technology, there were all sorts of interesting problems to be solved. Of course, eventually we did run out of steam with optical lithography, and today we're in the era of EUV lithography, which after decades of work finally made its way into high volume manufacturing 2-3 years ago. And it's what's used predominantly for leading edge technology today. As with all prior generations of lithographic technology, we want to extend it. And there are all sorts of fascinating problems to be addressed by lithographers today. We have the issue of stochastics, important for yield, as well as parameters that are affected by line edge roughness. People have worked, again, decades to reduce defects on EUV masks, and more work continues to be done there. We have the problem of mask 3D effects that becomes increasingly important as we go to smaller and smaller features. Cost has always been a concern for lithography, and most definitely so for EUV lithography. I saw an estimate out on the internet the other day saying that a single high-NA EUV tool is expected to cost $340 million. Pretty incredible. There are also, I think, a number of interesting problems to be addressed for lithography at larger feature sizes. For example, in the area of silicon photonics, the feature sizes are hundreds of nanometers in size, but they often involve very complex curvilinear features and need exceedingly low line edge roughness. So I think that even though the features are large, there's some interesting problems for lithographers to solve. Packaging is also an area that's growing, and there are lithography issues to be addressed there, even though the resolution is only now getting to be a submicron. But I think it's very important because it addresses problems in system performance and addresses some of the cost issues that we have, especially with EUV. It's also a good time for our industry in that we are growing. The business is doing quite well, and I think that's really important because by having a nice revenue stream, we have the resources to fund the R&D, to create new generations of technology, and then to build the manufacturing facilities that we need for new generations of technology. So overall, I think this, lithography has always been exciting, continues to be so, and I think will be for quite some time.
Okay, thank you, Harry, for that very interesting talk, and congratulations again. So today we have a great pleasure, my personal pleasure, of being able to have a talk with Mike Hermes. Mike Hermes is the Vice President of Mass Technology at Micron. And I think we're going to find out lots of interesting things from his background and what he knows about the leading edge mask making. Mike, welcome, and thank you in advance. You've been at Micron for 38 years. I understand that you started out as a yield engineer, and now you're vice president of mass technology. Very interesting, and must have been a rewarding career. Please tell us a little bit about what's happened, what you've seen, and what you see going forward.
Thanks, Aki. It's great to be here. I'm actually relatively new to the mass side of the business. My first 32 years were on the wafer fab side. When I started in 1984, Micron had been making DRAM about 3 years and had about 600 employees, all here in Boise. Today, Micron's a global company with more than 40,000 employees and 28 billion in revenue last year. Micron's main products are NAND and DRAM memory, whose total worldwide market was greater than $160 billion last year. But the semiconductor memory history has been a roller coaster. In the 80s, when I started, Micron was a pure DRAM manufacturer. And I think there were maybe 18 DRAM manufacturers in the US at the time. Mm. Today, Micron's the only US-based DRAM maker left. It was in the 90s that Japan, with their manufacturing efficiency and innovation, they dominated DRAM. And it was during this time, I think there were roughly 10 Japanese DRAM manufacturers. There aren't any Japan-based companies still making DRAM. In the new millennium, Korean memory companies emerged as major players, and NAND emerged as another major memory type. So you're probably asking yourself, why have there been so many memory maker startups that ended up exiting the business? A big factor over the years has been these boom bust supply versus demand cycles. Every 5 or 6 years, there would be this bust cycle, prices would bottom out, and there would be casualties as a result. However, in the last 10 years, things have been more stable. The main DRAM players have been constant in the last 10 years. They are Micron, Samsung, and Hynix, who between the three have about 90% of the market share. On the NAND side, we have that same three, plus 3 others, Intel, WD, and Kioxia. Kioxia was spun off from Toshiba a few years back, if you recall. As we look forward, the wild card is China. Will its entry into semiconductor memory upset our supply-demand balance? So moving forward with personal highlights, joining the mass team about 5 years ago is one. I'm lucky to be surrounded by some fantastic, experienced mass experts who continuously educate me. Before that, I was fortunate enough to work in some pretty diverse parts of the business, wafer yield, as you mentioned, R&D fab operations, and process integration on an emerging memory technology. I once even led a Micron LED startup operation.
LED, huh? That's great. Yeah, yeah, yeah. Well, such a varied career. That's very interesting. Yeah, thank you. You're talking about your mask shop, and it's I'm sure it's a lot of work to manage one mask shop, but you have two mask shops, right? And what's the reason for having two? It is like going into UV and preparing for that one of them, or are there other reasons for having two mask shops?
Yeah, well, to keep up with leading edge wafer technology, you need to invest in leading edge mask tools. A few years back, we were in this position where we needed to bring in leading edge mask tools, but we were out of mask cleanroom space. Rather than displace the older tools with new ones, we elected to keep the legacy tools and built the second mask fab. Doing this enabled Micron to bring all the mask making in-house, which also enabled us to have more control over the mask costs. With regards to your question, does the second fab have to do with EUV? As you know, EUV and optical share a lot of the same process tools, but EUV also has some specialized tools, especially in the inspection and print validation areas. The bottom line is we run EUV and optical in both our mask fabs.
Mm-hmm.
Both fabs are here in Boise, so sometimes the mask will move between the two fabs for processing. Which brings up a win I'd like to highlight is how we've overcome logistical challenges to perform as one team across the two mask fabs.
Mm-hmm. Yeah, yeah, yeah. Well, teamwork is always an important thing, right? Yeah, that's so true. So on EUV, EUV masks have certain differences, even though they tried really hard and they succeeded for the most part in being able to use the same infrastructure for both, and that was important for having a smooth bring up in EUV, I think. But it seems like Micron's picked the right timing, for EUV. Now that pellicles are becoming available, and actinic inspection, like you mentioned, inspection as an important component. Was that on purpose? Tell me a little bit about that.
Yes, so you're right. Micron has a history of targeting the timing sweet spot when it comes to new technology, especially when there's a huge capital expense. So we've waited for some technologies to mature a bit before committing. A good example is the delay of 193 lithography adoption. We were able to extend 248 litho longer than our competitors with the use of high transmission masks, which was a novel technology at the time. Micron's also a pioneer in pitch multiplication. Our expertise in this area is one reason we've been able to delay the transition to EUV. With regards to EV pellicles and EV actinic barriers being removed, I still see issues with both. Both incur very high costs. EUV pellicles are not only costly, but they have short lifetimes, and they significantly reduce the throughput of the most expensive tool in the wafer fab, the EUV scanner.
Yeah, yeah, yeah. So there are more challenges, but that's an opportunity for many of the suppliers too, right? And it seems like there's no question that the world is committed to EUV. So now it's just a matter of continuous improvement, it seems like. Speaking of that, a curvilinear shape for EUV is something I'm, personally involved in and really curious about. I think Micron is entering EUV before high-NA, and so you would think that there's even more reason to use curvilinear shapes for EUV. What are your thoughts about that, and how is it going with Micron?
Yeah, so Micron's previously stated that curvilinear is a path to increase process margin and manufacturability in the context of immersion lithography. So it's natural that these methodologies would cascade to EUV. So whether it's assist features, curvilinear, or really whatever, you're going to use all the tools you have in your toolbox to get the most process margin possible. The infrastructure to support curvilinear will definitely be more mature when high-NA becomes available. So maybe that's the intersect point for broader adoption. In in the meantime, curvilinear continues to evolve, and we'll continue to develop and process curvilinear shapes. But today, it's still very resource intensive.
Right. So it's ramping up, basically, right? Speaking of that, curvilinear in general, and EUV for that matter too, the eBeam initiative conducts a annual luminary survey, and in the last couple of years, it's come up. The reason for multi-beam based mask writing, the number one reason people say is EUV, and then number two reason basically is for curvilinear, and that's for curvilinear for either EUV or 193i is what the luminaries seem to say. You haven't started production with EUV yet because you have all these other technologies that enables you to extend 193i. Why is it that you have multi-beam writing capability in a mask shop now?
Yeah, so multi-beams enable higher quality reticles from a local CDU and a registration standpoint. You're going to want this whether it's on EUV or optical. The multi-beam reduces the mask contribution to placement error on the wafer. This is important because over time, the overlay tolerances have continued to shrink and become more critical. Micron has been developing EUV for years. However, past masks did not have these ultra-high figure densities. Today, some EUV layers will have higher figure density, and for these, the write time on a variable shape beam can be days or weeks. So for these, multi-beam is a necessity. I should also note that multi-beam also enables low sensitivity resist, which would also lead to days or weeks if you were writing on a variable shape beam.
Yeah, so placement accuracy is an important factor for everything, including 193i, and so that's a good reason. That's not in the survey question, so maybe we should add that. But okay, great. Curvy things. We've been talking about it a little bit, and Micron's clearly been leader in the use of curvilinear shapes for masks, and but other people are now definitely getting into it, right? It's kind of the talk of the town. Do you have any advice for other people? Having been the kind of blazing the trails, as it were.
Yeah, well, I think in general, the industry infrastructure to support the application of curvilinear is still immature. Users are still trying to figure out where OPC, MPC, eBeam writer, and inspection tool formats will eventually land to ensure efficient interoperability across the tools and the technologies. There's multiple efforts in this area with the extended OASIS format, the MBF 2.0 file format, and we see other proposals from EDA companies. But I wish we were seeing a little more traction and convergence to a default solution that the industry can adopt and move forward with. I am encouraged to see a curvilinear task force was recently formed by the Semi Industry Association. Another thing to consider is that full field curvilinear processing requires a lot of computing power, especially if you want to achieve the desired throughput. There are absolutely opportunities for innovation in this space. What we see today is the application of curvilinear is restricted to areas with high pattern repetition. You see, with these repetitive patterns, you can contain the processing requirements, so you're getting a reasonable ROI. This is a great opportunity for the industry. Bring the users and vendors together, have them collaborate to advance the state of the art. Aki, I'd be happy, along with the eBeam initiative, to participate and bring everyone together to make this happen.
Oh, that's great. Really appreciate that. And I appreciate your encouraging words about the opportunities that's there, because that's part of what I spend my time doing too. And yeah, it would be great for you to be able to help the whole industry, right? Bring up faster and smoother. I think that would be great. Yeah, so that's really exciting by itself. But the mask industry, the semiconductor industry, things are going on, seems to be resilient to COVID, even though those of us working in it, have to fight it, right? But how do you feel about the future of the mask industry?
Yeah, well, working in the leading edge of mask technology with things like the multi-beam, actinic inspection, and curvilinear is really exciting, really extremely exciting. Photomask development is a key enabler in achieving the technology advancements that we need on wafer. Because of this, we always need to be thinking ahead of the curve, anticipating the needs that will come with each shrink or each new light wavelength. There's incredible growth in today's data economy. So we at the Mask Shop have a huge hand in keeping up with those demands through innovation and collaboration with our wafer fab partners.
Yeah, here. That's it's great. I too enjoy being in this industry a lot, and being able to speak with you and understand your background and all that. That's the kind of pleasure that I enjoy a lot. So thank you very much today for giving us some of your insights and your background. Really interesting. LED, right? That's great. Yeah. Okay. Thank you, Mike.
Thank you.
Well, that was an incredible honor to be able to talk with Mike, and then hear from three Frits Zernike Award winners, past and present. And thank you very much for attending today's meeting. Hopefully, we'll be able to see each other in person next year. Thank you.